of the E-Cig 2021 Spring Technical Workshop. We have another great session lined up for today, looking at what's going on in the wonderful world of transmission. I'm Charlie Smith, the Executive Director of E-Cig, and I will provide a few brief opening remarks. As you know, our spring workshop sessions are all being held online and are open to everyone. The workshop was planned with the input of our E-Cig Offerings Committee, chaired by Bethany Frew of NREL and Julia Matoy-Basan of ERCOT. The committee consists of the chairs of our 6 working groups and several of our board members. We have a great set of volunteers who really make E-Cig what it is, and we encourage you to become involved if you're not already. Regarding logistics, I would ask you to note that the webinar will be 90 minutes long. We had a lot of feedback that our 1-hour workshop sessions were too rushed, so we're experimenting with some longer formats for the spring workshop. Our revised format today will have 3 individual presentations of approximately 20 minutes each in the first hour, followed by 20 to 30 minutes of Q&A after the last speaker. As we're doing with all of our webinars now, we'll be using the Slido platform for managing the Q&A, not the WebEx platform. You should go to slido.com on your device and enter E-Cig25 as the event code to ask your questions. Please be sure to indicate the person to whom you're addressing the question. The instructions are also in the background slide for the webinar, and you'll be reminded by the session chair. You'll see a thumbs up button next to the question on Slido to allow you to vote on prioritizing the questions submitted. So please keep the questions coming during the presentations, and we'll address them at the end. We'll follow up with written answers to any questions we don't get to during the Q&A. Recognizing the limitations of a webinar with more than 100 people on the lines will be muted. So again, we ask you to use the Slido platform to ask your questions with E-Cig25 as the event code. Today's session is titled Transmission, Breaking the Logjam. There's a growing realization that transmission is a critical link in the process of making the transition to renewable energy and decarbonizing our energy supply. Today's session will build on the transmission workshops and webinars we have held over the last 6 months. Looking at a future where most of our generation could be coming from large blocks of remote resources characterized by variability and uncertainty, where there is a critical need to move the goods to market, this is clearly an important topic. The session will be chaired by Wayne Galli of NextEra Energy Transmission. Wayne serves as the Executive Director of Development for the NextEra Transmission Group and has a long history in system planning, operations, market design, and transmission project development. He's a good friend of E-Cig and is well known to many of you. We're very happy to have him here with us today. Wayne, we appreciate your participation, and I'll now turn it over to you.
Charlie, and if anybody that's here was on yesterday's call, you know, Charlie and Bob Savdale exchanged some jabs about their lengthy tenures in the business. So I just noticed he mentioned my long history, but I'll save the jabs for over a beer, Charlie. Anyway, thanks for joining us. I'm excited about today. I'll keep my opening remarks very brief here and get right into the presentations. As Charlie said, please use the Slido platform as you ask your questions, and we'll get to those during the Q&A session at the end. Each section will be about 20 minutes, and then we'll have hopefully 20-25 minutes for questions and answers. So with that, we'll just dive right in. I think we have a nice mix of topics today, from kind of some neat analysis, some practical application, and some novel ideas for moving us toward kind of a carbon-free grid. And under the current administration, I think some of these applications here, we know it's going to be a hefty lift to get there. So to use a baseball analogy, I think we've got to hit some singles and get a high on-base percentage before we start swinging for the fences. So I think some of these presentations lend themselves to that direction. So with that, our first presentation is by Morgan Putnam. He is the principal at NGI Consulting. Morgan has worked in consulting and product development roles for software companies serving the solar and utility industries. He's advanced the interconnection process for distributed solar assets, developed financial products for utility-scale solar assets, and highlighted the value of overbuilding renewables to address seasonal energy imbalances. Morgan holds a PhD in chemical engineering from Caltech and a BS from Cornell University. So with that, Morgan, it's all yours.
Great. It is wonderful to be here today with everyone. I'm a huge fan of all the work E-Cig has done over the years, and so just honored to be able to be part of a workshop. I think this is not probably starting with a single. This is probably starting with a swing for the fences, and so we'll dive in on that. But I'll try to show some singles along the way. So we got a little bit on myself just now. I could sort of call out a couple additional things. Improving the interconnection process for distributed solar assets. That's something I worked on, automating technical screens with SIME, Synergy, EDD to tie into the Power Clerk platform at Clean Power Research, which manages about 40% of interconnections for distributed solar assets across the US. And that work has really helped me understand the challenges we're going to face as we look to add more and more assets to the grid, because it's given me insights into the technical challenges of adding distributed energy resources to a grid that was sort of built for one-way power flow. The other thing I would call out is my work with the Minnesota Solar Pathways Project. So that was work that highlighted the opportunity to deliver resource adequacy through overbuilding renewables and curtailing excess energy. And while transmission wasn't a focus of that work, it was certainly something that highlighted the need and opportunity for new transmission to help address high penetration renewables challenges. So kind of based on that experience, I decided at the start of 2020 to take a swing for the fences and try to think about public policy that aligned a few different things based on that prior experience in mind. And in particular, I felt that we needed to bring more stakeholders to the table and try to value stack various societal propositions in order to get new transmission built. And the obvious one, or what I thought was an obvious one, was transportation electrification. And I thought that because of the fact that the transportation system offers an existing right-of-way that we could possibly utilize to address siting challenges that transmission faces. And it's also an area where we're going to need to invest in the grid in order to enable transportation electrification. And there's been a few different studies that have shown that. There was good work by the West Coast Clean Transit Corridor study. There was also great work by Seattle City Light and RMI back in 2019. So, I wrote a white paper that tries to essentially tell that narrative. And in the process of writing that white paper, I realized it's actually not just the commingling of our energy infrastructure with our transportation infrastructure. It's also the commingling of our communications infrastructure with both sets of those other infrastructures. And in particular, to try to drive that point home, over the last 5 years, $150 billion have been invested in electric, connected, and autonomous vehicles. And so when you think about the future of transportation, it fundamentally requires much tighter integration between the transportation infrastructure and our communications and grid infrastructure. And I would say that the integration we have today is basically what's needed to run a gas pump. And then that just simply isn't going to cut it as we look forward. And in terms of societal benefits and sort of value stacking with regards to getting new transmission built, I think the other thing to do is to tell a story around technological leaderships and job benefits. So there's obviously construction benefits, and that's the reason there's sort of bipartisan interest in infrastructure. But there's also technology leadership opportunities. We've ceded 5G at this point to China. We have ceded HVDC transmission to China at this point, but we could be world leaders in this technology if we chose to be. So I'll jump ahead and, the next slide, I'll say, I'm not the first person that's thought about co-location. That's probably not a shock to those on this call, especially those who've been in the transmission space for a long time. And we certainly have elements of it in our grid today, but there are opportunities to, go further. And, to that end, Congress asked FERC to deliver a report on the barriers and opportunities for high voltage transmission using existing transportation right-of-ways. And that report was delivered in June of 2020. I think overall, in my personal opinion, it was fairly non-committal, but it didn't produce any, unsurmountable barriers. And it showed some examples of states that are already taking action to try and obtain this type of co-location. So you can see that Maine passed a law in 2010, basically designating energy corridors for the development of transmission and other energy infrastructure along specific highway and pipeline rights-of-way. New Hampshire, sort of similar for highway rights-of-way, where infrastructure would be underground for transmission and or other infrastructure like pipelines. And there are other states that allow this type of work. Wisconsin's another one. But the point basically being that there are no barriers to this. It's really just whether we have the political will to execute it. And some states have actually reached that consensus and political will. So I want to talk about transmission development today just for a brief moment. This is a figure from a great report, Macrogrids in the Mainstream, that's produced by Americans for a Clean Energy Grid. Obviously a bit of an eye chart on the left. The key thing is that there are sort of 4 blocks. The first 2 blocks take about a year or 2 each to get through, as this is a process flow diagram with regards to building new transmission. And then the 2 blocks on the far right take about 3 to 5 years to get through. And so the first of those is sort of a NEPA block, and then the second one is sort of going through the various state approval and federal approval for transmission siting. And you know, the joke I make is, to put it in layman's terms, this process for new transmission is go to jail, go directly to jail, and do not pass go. What I think is notable is that the Trump administration did simplify the NEPA process and has essentially reduced the timeline for block 3. And if you look at if you were to squint, it's not visible on the slide, but look at the very start of the flow diagram for the 4th block, what you can see is that if you're just on federal lands, like you would be in the case of highway right-of-way, you basically can just skip this process and go straight to build line. And so I think that's really where the opportunity is to cut a lot of the transmission development timeline down, is to take advantage of the existing changes to NEPA. Obviously, some of those are controversial and probably get adjusted by the new administration, but the streamlining, I think, is something that people can agree on is an important thing to do, and having some fixed timelines. And then secondly, you know, the federal interstate, to the degree that we can have utilities work with departments of transportation, offers a very unique right-of-way. And I've been talking about this co-location with regards to energy infrastructure and transportation infrastructure, but I want to call out that there's already been a decade plus of work to co-locate communications infrastructure with highways. And that is sort of broadly known as Dig Once legislation. It's been passed at the state level, not yet at the federal level. The states that have passed it are fairly politically diverse. So we've got California on the sort of far left of the country, both geographically and a bit literally. And then we've got you know, West Virginia over on the right side of the country, and also sort of politically leaning to the right. So, you know, this is something that states can agree on because of the fact that it is a cost-saving measure that helps deliver something that's an important national asset, which is broadband to all Americans. And that's something that, you know, 2020 only, you know, highlighted the need for broadband access. Okay, so what would one do if they could co-locate transmission in the highway right-of-way? I think really the first thing one would do is they would look quite seriously at constructing a national HVDC transmission grid. You know, HVDC is something that I think has gotten a lot of attention recently over the last year or so, and that's because there's been significant advancements in the technology over the last 10 years. And so what we have here is one of the scenarios that NREL modeled in their interconnection seam study. The black lines are a national HVDC grid. The blue lines are the interstate, and you can see that there's fairly good overlap in these 2 sets of lines, that you could utilize the interstate to build out this national HVDC grid. Now, cost is really, I think, the main barrier that people consider with regards to HVDC. I'll talk about that briefly here and then a little bit further at the end of the presentation. I just want to start by noting that in NREL's study, they found that there was $1 to $2 in net benefits for every dollar invested in an HVDC grid, and that grid helped enable very high renewable penetrations. So, you know, the general cost metric, and, you know, there's a range for sure, but the general cost metric I like to use for the difference between overhead and underground is 2x. 2x means that this grid still pencils, even if you go underground in the interstate right-of-way. And whereas I'm not sure, in my personal opinion, that you can build an overhead national grid, I do believe you can build an underground national grid. And that's really what we're seeing Germany do with their SüdLink and SüdOstLink lines. You know, they spent a decade trying to do the overhead approach with HVDC, and they said, it's not going to work, we're going to go underground. And so I think that this is really the first opportunity for co-located infrastructure. The second, I think, is in urban areas. And what I'm showing here are a transportation project and a transmission project in the greater Seattle region, which is where I happen to live. So I get to pick on my home state here for a moment. And what you're seeing are 50-year infrastructure investments that started within a year of each other. So the transportation project started last year. The transmission project started this year. They're fundamentally doing the same thing. They're moving either cars or electrons from south of the Seattle region up into the east side of it, the Bellevue, Kirkland area. And, you know, what is notable here is that these investments do not consider each other. And they, you know, they are even more siloed than generation, distribution, and transmission are siloed within the utility industry. And so to kind of give you a sense of that, the master plan for the highway is from an EIS that was created in 2002, and electric vehicles are not contained in that EIS. That's despite the fact that the county this project sits in has a goal for 100% transit electrification by 2040, and then that goal, according to our RMI, will require 9 of 11 substations to be upgraded. Similarly, the East Side transmission project, if you look at the siting analysis that was done for it, they said, you know, we could site along the highway, but wait, that's not possible. You can't work with DOTs. It's a little bit more politically sensitive than that, but you know, that's more or less the short version of it. It's not possible to work with the DOT. And that's something that I've heard a number of utilities across the country express frustration with. And I think what is really a fundamental challenge that we're going to have to address collectively if we are actually going to solve the transportation electrification challenge. Because even if we're not co-locating extensive amounts of transmission with interstate and highway right-of-way, we're going to have to do enough integration that we've got to improve that relationship. So, you know, in terms of singles, doubles, and home runs, you know, your home run is sort of this right here. And I think your single is improving the relationship with the between the utilities and the DOTs. And I think it's really going to require governors to get involved on that front. You know, I was talking with a utility in Washington State, and they said, hey, you know, it's great that you want me to work with the DOT, but they just told me to move my infrastructure out of the highway because they now have increased safety standards. And so that's, it didn't sound like a productive and healthy dialogue that sort of exists today. So barriers to next-gen highways, I was just starting to touch upon this. Safety is a big reason why we don't have co-located infrastructure today. You know, essentially the DOT's number one, or one of their number one priorities, is to protect vehicles that leave the roadway from colliding with objects. That's why you see significant various barriers whenever there is an actual collision risk, like a bridge abutment. Another one that's been historical is the expansion of the highway. So, you know, we need to preserve the right of way for future expansion was the mindset 20, 30 years ago. It's really no longer the mindset. I want to be conscious of time here. I think I've got about 5 minutes left. Is that correct, Ryan?
You've got about 8 or 9 minutes left.
Okay, perfect. Thanks. So how do we overcome these barriers? Well, the first thing we need to do is we need to start updating DOT utility accommodation manuals and processes. I think the second thing we need to do is increase coordination between DOTs and utilities, and really those first two go hand in hand. And then third, I think we really need to think more and more about going underground with direct current transmission, possibly medium voltage direct current transmission in urban areas to support transportation electrification. This was something that Southern California Edison alluded to in a white paper that they released in December, as well as high voltage direct current for long distance transmission. I'm actually going to skip this slide, so I'll jump to this one, which is organizations have expressed interest in further exploration of the next-gen highways concept. You can see sort of a wide variety of folks on here. I will call out that there are folks from the energy industry as well as from the transportation industry. We've got ITC, who's an independent transmission developer. We've got the Minnesota Department of Transportation. Notably, the Ray, who's a close partner of mine. The Ray is a name that I don't think most folks on this call will know. It's named after Ray Anderson, who's really one of the people who first put life cycle sustainability practices into really operationalize them with regards to the carpet manufacturing business. And basically he made his $1 billion carpet manufacturing business more profitable in the process. And so when he passed away, the state of Georgia said, hey, we're going to need a highway after him. And they did that. And then the family said, oh, wait, we've just named one of the dirtiest pieces of infrastructure after someone who was, a pioneer in sustainability. So the Ray was born as a partnership between Georgia DOT and sort of the family foundation to figure out how to make highways more sustainable. And today they work with over 30 different DOTs in 14 different states. And so, as we think about improving this relationship between the energy industry and the DOTs, to my mind, the Ray is going to be a really critical organization in supporting that transition. The recent support for elements of next-gen highways, I alluded earlier to the work by Southern California Edison. I would note that former U.S. Deputy Secretary of Transportation, John Picari, has come out as a significant supporter and advocate for Hvdc in the highway right-of-way. He testified in front of the Commerce, Science, and Technology Senate Committee yesterday. He authored, along with the Ray and Jigar Shah, Peace in the Hill at the end of December. And so we do have advocates. FHWA leadership yesterday was saying that they are looking not just at improving EV charging opportunities in the federal interstate, but also at improving transmission access. And, I would note that now Secretary of Energy Granholm in her Senate confirmation hearings, spoke to this chance to do, this opportunity to do expanded dig once, where we are not just doing fiber, but we are also doing transmission. Okay, cost. I kind of touched upon it earlier. It is I think, one of the biggest concerns in the room, especially for those in the utility industry who've basically written off HVDC as always costing too much. I'm going to show material here from Direct Connect development company, the developers of the Sioux Green Line. This is one of a few different slides that they have where they compare their estimated project costs with various other types of public data that's available for overhead HVAC and overhead HVDC. And what you can see here is that when you look at a dollars per megawatt mile basis, so normalized to capacity is important, you can see that the underground HVDC is cost competitive. Now, I understand that that's obviously the opinion of a developer, and so it's also an estimate. We don't have a firm number on this. I think, frankly, one of the things that the DOE Loan Program Office should do is help us to get a firmer sense of what the costs really are by enabling us to build one or two of these projects. But I think it's also important to talk about benefits, because overhead and buried are not fundamentally the same value proposition from my perspective. I think that buried is much more weather hardened than overhead. I think that we have the option to EMP harden buried transmission, and EMP is a real risk. North Korea has capabilities to deliver an EMP attack, and Department of Defense estimates as to what that attack would do to the country are not pretty. Permitting timeline. I think we can go faster with buried in the highway right-of-way, as I alluded to earlier, and land use. Obviously, if we're talking about greenfield overhead, that is something that has significant land use impacts, whereas buried in an existing transportation corridor would not. And just to kind of put a picture on some of this, severe weather events. This is Hurricane Laura. It's damage to the energy service territory. All 9 transmission lines were currently out of service. A significant number of transmission structures were damaged beyond repair and require complete replacement. At E-Cig and other organizations, across the energy industry, we like to talk about flexible resources, but I'm pretty sure that a transmission line that is bent in half is not what we consider to be a flexible resource. Small attempt at humor. Wildfire risk. These overhead lines don't just have a risk from severe weather events, they have a risk of creating problems. And so in the Kincaid fire, which was the largest fire in California in 2019, A PG&E transmission tower is the believed source of the fire, according to CAL FIRE. And this was an event that left 3 million people without power due to broader system de-energization that was taken as a result of the fires. And lastly, you know, we've all talked and thought a lot about the events in ERCOT a month ago, but if everything's electric, outages are all the more significant. You know, I grew up in Minnesota. I know what a cold day looks like. And if we are dependent on heat in order to, you know, get through the winter months, then we need that to be, we need a certain amount of it to be available. All right, so my last concluding thoughts on breaking the transmission logjam. First, implement common sense transmission reform. There are many great people who know significantly more than I who have been working for years to improve the transmission process at the federal and regional level. Calling out Americans for a Clean Energy Grid is calling out but one of the many folks who are doing stuff in this space. I would say that secondly, and this is something that I'm a big believer in and I'm trying to advance with the Next Gen Highways concept, is building a coalition of supporters outside of the electric sector. And then step three is really have a lot of eggs. So, you know, when I speak to Rob Gramlich, one of the things that he talks about, what they're trying to do is they're trying to have a lot of different ways to enable new transmission. And so I like to think about E-Cig's eggs and then my one little Next Gen Highways egg. And so with that, I look forward to being part of the panel. Thanks so much.
Thank you, Morgan. And again, to those listening in, the questions are coming in on Slido. Feel free to vote for your favorites or add your own. So next up, we have David Quier and Joey Alexander to talk about some dynamic line rating opportunities that are currently ongoing. David is the Director of Asset Management in the Transmission and Substations Organization of PPL Electric Utilities. In this role, he oversees planning, system reliability, standards, strategic initiatives, regulatory policy, special projects, and capital development. Joey is the Director of Business Development for Ampacimon, North America, where he provides dynamic line rating solutions to the U.S. and Canadian-based utilities. Joey has extensive experience in the energy sector with a background in renewables and sustainable energy products, energy storage, and smart grid technology. He earned his Bachelor of Science in Chemical Engineering from the Georgia Institute of Technology and a master's degree in Business Administration from Emory University. So with that, David and Joey, it's all yours.
The introduction, Wayne, and I'm honored to speak at this panel. So I'll just get right into it. At PPL, you know, we're really looking to embrace dynamic line ratings as technology that, you know, we can leverage to increase reliability, but then also balance that with driving down costs for our customers. You know, we could continue to build out the transmission system and continue to attain better and better rates of reliability. But there's only so much you can do before you start to impact customer rates negatively on the affordability range. And so it's a balance there. And we see dynamic line ratings as a technology that really enables us to achieve both where we can use it. Next slide, please, Joey. Thank you. So we had two lines in our territory that we identified last year that basically had two different things going on with them. The first is asset health. So they were conductors that were decades old. And when we're going through our asset health decisions at PPL in our different asset classes like conductors or poles, transformers, breakers, et cetera, you know, you get into the situation where you're basically trying to predict when something's failed so you can optimize both your investment strategy as well as your maintenance. For conductors, though, we really realize that we don't have that much data on what is going on with our conductors, what the health is, what temperatures they've been operated to, what conditions they've lived in, as much as we have for a lot of our, say, substation equipment and even a lot of our distribution equipment. So we had two lines that both had asset health issues or were starting to at least enter that territory, combined with they had congestion on them. They were our Juniata, Cumberland, and Harwood Susquehanna lines. This slide really zooms in on the Harwood Susquehanna lines, but essentially that was the issue at hand. Two lines, decades old, both with congestion. And so we looked for opportunities where we could leverage, you know, what was at minimum a new technology for at PPL and see if we could alleviate our own internal concerns and the congestion at a very cost-effective manner for our customers. So getting the solutions, thanks, Joey. The first two, the reconductor or basically the rebuild, those are our typically two go-to. So if there's going to be congestion on the line, and we're going to work with PJM, who runs the market efficiency windows, and if we're going to have to alleviate congestion through a project, the go-to projects are reconductors and rebuilds to some degree of that line, and you're getting to a good amount of cost. You're starting to get into the millions per mile, and the benefits are there capacity-wise, and you've refreshed the asset health of that asset. But even besides the cost, there's also the community impact. So where we have to go through the external communications of notifying people that we're going to be working in what could essentially be their backyards, and it can be somewhat disruptive to the communities and dealing with these projects and things like that. But the fact that dynamic line ratings and then working with Ampacimon, we were able to confirm that, hey, we can actually gain asset health of these lines, and we may be able to alleviate the congestion that has become an issue with them. It was really a no-brainer for us to pursue. When you do the benefit to cost ratio on dynamic line ratings compared to these projects, it's always going to be a win for customers if dynamic line ratings can solve the issue. So we aggressively pursued, worked with Ampacimon to pursue this technology on these two lines. Going into our ratings, one of the things, when we go through our ratings methodology, static line ratings, which are how we establish our line ratings, are basically very conservative. We have to, especially our normal ratings, we're basically assuming 0 wind speed, the worst ambient temperature, we're only toggling it for certain seasons. And we have to make sure that we're operating our system so that the lines never burn down. So we're always going to assume worst case, which is the lowest rating, which then also drives us not to be able to optimize our system as much as we'd like to. Dynamic line ratings basically allows us to eliminate those assumptions. We're getting wind speeds, we're getting the ambient temperature of the conditions that these conductors are in. We do have a hilly terrain, so our transmission lines are along rivers, they're up and down mountains, or they're in farmland across Pennsylvania. And so, much different conditions for our lines, but under static line ratings, they basically are all getting similar ratings. To have wind speed, ambient temperature, the actual conductor temperature, and then also conductor sag through vibration, we can eliminate that conservatism and maximize the use of our system that we've built. And next slide, Joey, please. And so one of the things that we also worked with in Ampacimon, and this was a learning for me, I'll say, is when you look at what our static rating has been for say a line, and then you look at, okay, if you adjust upward based off of having accurate ambient temperature, you increase your rating by a good amount for most of the year. But it's when you really add wind that the rating significantly increases that much. And so, that was what we really appreciated from working with Ampacimon. We basically studied the aspects of these specific lines. So we obtained a customized studies that showed what the predicted ratings increase would be with just ambient temperature and more accurate real-time data. But then when you leverage on wind and you see how much area under the curve you increase by, it's pretty impressive. And it really enables us, it gave us the confidence to proceed with these projects, and we're starting to reap the gains of putting these sensors on the line. I'll turn it over to Joey for some of the next few topics. Oh, I think we can't hear you, Joe.
I think you're muted.
Maybe if Joe.
Hear me now? Can you guys hear me
Yes.
now? Oh, great. It was not a fatal error. It was just a problem with my selection of my device. So yeah, thank you so much, Dave, for taking us through the background of the project. So I'm Joey with Ampacimon, and We were the DLR solutions provider in this project, and I'm going to take you through just a few slides on the process that we go through with customers in designing and deploying a dynamic line rating system. So it's good we're on this slide with wind. I'm going to stick on it for maybe another minute, but yeah, focus in on that orange square for wind, because when it comes to dynamic line rating, wind is key. You know, and especially the perpendicular component of the wind speed, as you see the 90-degree angle. So if you think about, you know, if you think about this from fluid flows and convective cooling, this is the wind that's going to have the highest impact on cooling your line. So much so that, you know, just 1 meter per second of perpendicular wind can almost increase your capacity by 44%. Okay, so that's a really positive thing. The scary thing about wind is that wind is extremely dynamic. So unlike ambient temperature, which is fairly homogeneous and predictable, wind changes very readily depending on elevation. So the wind that the conductor is experiencing can be quite different than the wind that's going on the ground. You know, at the same time, you know, if you think about taking wind data from, you know, wind or weather data systems like IBM, which are great, you know, that data is coming from probably an airport weather station, and they're interpolating what the wind is in an area that it probably doesn't know how to do that. So it's really important that wind is accurately measured as it impacts the line, and also that there's an accurate assessment of specifically the perpendicular wind that's crossing the line, because that's what gives you the highest impact. The risk to using wind, the power of wind here, and you know, these are all different environmental variables that are used in all the different standards-based dynamic line rating models. So wind is used in all of those. If you get wind wrong and you overestimate wind, then you're at risk of rating your line way too high, and that could be an unsafe condition. So making sure that you have a really good handle on what that wind speed is, measuring it as it impacts the line is extremely important. All right, I'm going to advance the slide. Okay, so this is just kind of a high-level block diagram of how dynamic line rating works in terms of measurements and data flow. So starting out on the left side of the screen here, you have a sensor there. So this is our sensor for higher voltage lines like we have on PPL's lines now. And primarily it takes two different classes of measurements. The first of which we call line measurements. And these types of measurements are really used to make sure that we're staying within the limitations that are set by the utility. So you know, typically lines are rated based on a maximum conductor temperature and or a maximum sag. Okay, so these sensors on the line, they use line vibration. They measure line vibration to determine how much that line is sagging and also what the line temperature is. And that way we ensure that we're safely operating the line without too much sag, too much temperature. Also, the temperature is important because it gets fed into the thermal model for line ratings. The second class of measurements we take with this sensor are for weather. And that's to ascertain what's going on in and around the conductor that impacts the thermal model of that conductor. So the most important thing to measure here, like I said before, is wind speed. So using our vibration metrology that I mentioned before, we're able to translate vibration into wind speed. So as that wind, the perpendicular wind, blows across the line, it has a very specific signature in the vibration spectrum, and we're able to use some kind of fancy fluid dynamic models to accurately translate that into the real wind speed that's hitting that line. Okay, so all that data is fed into our operating engine for real-time ratings, and it's full of algorithms and models, but primarily based on the IEEE standard for line rating capacity. It's IEEE 738. Okay, and we also calculate forecasted line ratings. And the only way to forecast line ratings is to use forecasted weather data, right? And so as we all know, weather data forecasts sometimes are not exactly right. So what we do in our system to ensure accuracy is we employ a machine learning feedback loop. And what that does is it compares post facto what the actual weather measurement was from our sensor and compares that to what the prediction was, okay? And over the period of a few weeks, it develops correction factors to those weather forecasts that allow for much more accurate forecasts. So just to give you an example, let's say that we had been getting forecasted weather data that gave us, 2 meters per second of wind speed, okay? But the actual measurement that we've been comparing it to was 1.5 meters per second. So over time, we learned that there's a trend there, and we correct that wind speed down to what the actual wind speed is that was being measured. And that's just to ensure accuracy. So once we have real-time ratings, we have forecasted ratings, we pass those on in real time and typically in five-minute intervals into the utilities transmission management system. And then they can operate on that and use that data to pass on to other operational systems if they need to. Okay. Next slide here. So we do a pretty aggressive planning stage for our dynamic line rating deployments. That planning stage starts with the customer identifying the line, the line that they're targeting to have dynamic line rating on. And so we take in data, geospatial data, and also materials and thermal data on the conductor of that line. And we build a geospatial model of the line in 3 dimensions. And that's important because we're going to use that model to basically input historical weather data. So we're recreating the past of this line to see what the dynamic line ratings would have been had we had sensors on those lines at that point in the past. And so we input wind speed, wind direction, the ambient temperature, solar radiation into the model. And this is modeled out at every single span. So we're able to look at what the thermal model looks like for every single conductor span. And then output for the customer what the rating is, what the forecasted ratings would have been, and also all the different relevant weather statistics that we have from our data. Okay, and most of our customers use this to prove out business cases. They use it for downstream modeling, as PPL has done. But it's a really helpful tool for that, and as you'll find out in a few slides down, it's also helpful when it comes down to identifying target candidate spans to put sensors on. Okay, next slide. So here is some of the data from, here's some of the data from PPL's simulation that we ran for them. So there's Susquehanna-Harwood has 2 circuits. And so based on our simulated data, they're able to achieve a capacity greater than static 100% of the time between April and September, so the summer months. And then during the winter months, they're able to achieve a capacity greater than static 98.9% of the time. And one of the things they chose to do, just based on their realistic modeling, is to limit the gains, right? So they took our data and realized that we have some substation limitations that we need to pay attention to, so we won't go past that limitation. So based on the data that we were able to crunch for them, they got really good results. Average gains above static were between 25 and 29%, depending on the timing of the year. Okay. So one final thing we do for DLR planning is to determine which spans need sensors. So Dave may correct me. I think this line was around 20 kilometers, 79 or 80 spans. We don't need to put sensors on every single span. Really, the important spans to put sensors on are the ones that are going to be the most thermally limiting, that are going to be the bottleneck for that line. And so by the fact that we model out every single span of this transmission line, we're able to put on a distribution curve the percentages of the time that each span was the limiting or critical span in that line. And that qualifies those spans as candidates for sensors. We go one step beyond that, is basically we have a set of span selection rules that we've developed over the past 10 to 12 years, deploying these sensors all throughout Europe. One of the most important rules is that anytime your line orientation changes by 15 degrees, you need to have at least one sensor in that orientation. And the reason we do that is to ensure that we're getting all angles of the wind speed, right? So we want to make sure that we understand that wind component really, really well. And then also, we talk to the utility and find out if they have records of any spans that have been troublesome, that have had safety concerns, or that might be high risk because they're going over something. And ultimately, we come up with sensor locations. So for this line at PPL, we have 6 different sensor locations that we identified as the most critical spans to monitor here. Okay. And I think I'm turning this back over to David now. All right, David, take it over.
Yeah, no, thanks, Joey. So essentially, we did hang sensors on our Susquehanna Harwood line, as well as another line this past winter. I'd love to say that I have a lot of lessons learned to share, but it really was as simple and easy as you'd expect from hanging like a pretty straightforward sensor on a transmission line. It can be done live. For our first installation, just out of caution, we did take a 1-day outage just to make sure that we felt comfortable going into it. But then for the second installations and going forward, we have no inhibitions to nothing would block us from installing it live. So you actually don't need an outage to hang the sensors. We worked with Ampacimon for, as Joey was alluding to, of where the sensors should be placed and how many, but very quick and easy, and no real issues to report with the installation, and we were happy about that. And then our last slide, please, Joey. So upcoming work in getting into real-time ratings, it does introduce certain aspects that we really never thought of before. Like, for instance, well, if the ratings are obviously going to change based off of how fast or slow the wind is blowing and temperature and time of day, you get into questions like, well, how often will we allow the rating to change? And how drastically will we allow that rating to jump around? As well as, hey, if by some reason we would say lose communication to the sensor, what's our fallback rating, which, it pretty clear cut for that. We just fall back to our original static rating, but we just had to think through things that we hadn't had to think through before. We are working closely with PJM. PJM has been great as an RTO to work with, just to integrate it into their operations. Because I think in peer benchmark we've done on this to also just learn from other utilities. I think one of the things that's a little different than what we're doing is we are looking to take these sensors and embed them right into our core operations, as well as passing the information to PJM for them to use in their operations and other departments. And while I'm not qualified to speak on that, but like I said, just working with PJM has just been excellent to make this operational. And then last is, as transmission companies, we're very concerned with the bulk electric system security and reliability. And so NERC SIP compliance is always at the forefront for us. And so going through and ensuring that dynamic line ratings met our NERC and SIP standards that we're accountable for was also part of this work. And we still have some work to do going forward on that. So like I said, once again, I really appreciate Wayne and team for allowing us to present, and we welcome questions and comments.
Thank you, gentlemen. And last but certainly not least, our next panelist is Patrick Brown, who is recently a postdoc fellow at the MIT Energy Initiative and is currently a researcher at the National Renewable Energy Laboratory. His research focuses on improving the representation of renewable energy, transmission, and energy storage in long-term power system planning models to support rapid decarbonization. Patrick completed his undergraduate studies in physics and chemistry at the University of Notre Dame and his PhD in physics at MIT, where he was co-author of the MIT Future of Solar Energy Study. So with that, Patrick, it's all yours.
All right, thanks. Can you see my slides okay?
Looks good.
Yeah.
Okay, thanks. All right, so I'll be talking today about a study that my colleague Auden Butterud and I published a few months ago in Joule, looking at the value of interregional coordination and transmission for decarbonizing the US electricity system. So this study is part of a large and growing body of work on low and zero carbon power systems for the US. And at a high level, these studies can sort of be broken down into two main classes, although there are exceptions to that. The first is studies of low carbon grids that typically have high geographic coverage, sequential investment pathway, so plotting out the investment over time, but relatively low temporal resolution for capacity investment decisions. Another class is looking directly at 100% systems, but in this case, they trade the geographic resolution for higher temporal resolution. And so they're often of isolated regions or sometimes of a copper plate US without an explicit representation of transmission, but higher typically hourly resolution and greater than or equal to 1 year of renewables data. There are some exceptions. So Clack and McDonald's study kind of goes between these two, looking at many years of hourly data up to 80% emissions reduction. And then there's, particularly in the last few months, a continued release of additional studies that are kind of breaking down this divide, and also continued improvement to models like NREL's Reed's model and others to increase resolution. That being said, when you're looking at high renewables penetration, the temporal resolution and the transmission are both important. So in this study, we fall in this second camp, but are really focused on improving transmission modeling and on looking at the impact of geographic coverage and assumptions. So for that, we developed a model that does co-optimized capacity and operation planning for the contiguous US using 7 years of chronological hourly weather data. We focus on zero carbon as the central case. So that means we sacrifice some other resolution that you would need if you were not focused on zero carbon. And we take a pretty technologically conservative approach using technologies that are currently deployed at gigawatt scale. In terms of the geographic coverage, we do 3 major kind of scenarios that I'll discuss throughout this talk. The first is isolated states. So each state must balance its supply and demand within its borders. Second is 11 isolated planning areas. And so in this case, each planning area can build new transmission to adjacent states, but can't share supply and demand across borders. And then the main model is the interconnected US system, where we use some of the learnings from the isolated planning areas and then explicitly model the flows between planning areas across the US. So the other main motivation of this study, besides representing transmission at higher resolution, is to look at kind of a conservative case to say, what would it look like to decarbonize the US given technologies currently deployed at gigawatt scale? And the motivation there is really because if you're looking at decarbonizing in 15 or 20 years, which is what we need to do to avoid the worst effects of climate change, that isn't really much time to develop, completely new supply chains and take technologies up to gigawatt scale that aren't currently being deployed at that scale. So for the US, that's a pretty limited set of technologies, includes PV, wind, lithium-ion batteries, and then existing hydropower. We don't expand hydropower. And then we'll discuss a few sensitivity studies where we add additional technologies to the mix, including long duration energy storage modeled on pumped hydro, nuclear, and then natural gas in some sub 100% sensitivity cases. But we leave out some other technologies, so offshore wind and other technologies that wouldn't fit with zero carbon. That's not to say that we shouldn't work on these technologies. We certainly should work on them. But given their current low capacity, it can be somewhat risky to plan on them being available. And some of these would certainly be interesting to look at in future work. So just to reiterate, we're primarily focused on resource adequacy in zero carbon systems, looking at a pretty technologically conservative technology mix. And the study is primarily an improvement on a few aspects of some previous studies. So rather than doing a copper plate for the US or for regions, we do explicit interregional transmission flows. Instead of isolated regions, we look at the full US, and we consider 7 years of hourly resource and resource data combined with hourly load. Just to be clear about what this study is not, so we do not do AC or DC optimal power flow or security constrained dispatch. The transmission and generation are pretty highly aggregated. So with that in mind, it's also shouldn't be considered a transmission or generation siting study, just because we do have to aggregate flows at a very high level between states and between planning areas. We don't look a lot into specific policies, so we model just kind of a basic clean energy standard, but don't look into regulatory approaches for enforcing that. It's also not an economy-wide study. We're just looking at the electricity system, although we do consider a few high electrification sensitivities using demand from the NREL electrification futures study. And then finally, it's not a pathway study. So we're modeling 2040 hourly load, but we're not modeling, say, like every 5 or 10 years to get there. So it's kind of a steady state snapshot of what the system might look like in a future year, given 7 years of weather data. So just to give a quick overview of the method, one of the most important pieces here is the renewables profiles that we're using in the model. So to generate those, we start by identifying areas that could be candidates for a deployment of wind and solar. And those are the white areas, non-excluded areas in this map. Then we combine those with a map of the existing substations across the US and measure the distance from an array of PV and wind sites to those substations, and then come up with an interconnection cost map, where this dollars per kilowatt interconnection cost is added on to the PV and wind cost. So with that, we take the hourly resource data from over 40,000 solar sites and over 400,000 wind sites from NREL publicly available data, and then bin them either at the state level or at these 11 planning areas, and then bin them again based on the LCOE to generate aggregated hourly over 7-year profiles, which we then feed into our capacity planning model. And so just to be clear, since transmission is a focus, we're modeling transmission in kind of 3 different ways in this study. The first are these interconnection lines, which I discussed on the previous slide. For these factor into the cost of transmission, and they're basically added on to the cost of wind and solar in the model, but we don't explicitly model these flows or count them in the terawatt kilometer totals that we'll report. There's also the interstate intra-planning area transmission. So this first step is solving each planning area on its own, figuring out how much transmission capacity needs to be added to balance the wind and solar with load within that planning area. We then use that to calculate an intra-planning area transmission cost adder for wind and solar. And then we use that in the full US model as a cost adder for wind and solar across these different planning areas. But then we only model flows between planning areas at the full US. And so I'll break out these different costs in the following slides. So to get to the results, we'll start here with the isolated states case, which is really very conservative, saying each state has to go zero carbon based on renewables within its borders. And I'm showing here on the left the system cost of electricity. That's just the annualized CapEx and OpEx divided by the annual load, broken down into the different components. So hydro operations on the bottom, which is pretty hard to see, wind, solar, storage, which here is lithium ion, and then the PV and wind interconnection costs at the top. And then over here, the interstate transmission capacity. And since these are isolated states, there's nothing showing up here. So as we go through and add additional types of transmission to the model, we see that the system cost of electricity continuously declines. So this here is moving just from isolated states to the existing regional, so within planning area transmission. Then we can say allow new transmission between states just within the planning areas, so not yet between planning areas. By doing that, we spend this small sliver up here of about $0.8 per megawatt hour of new transmission costs, but then reduce the system cost of electricity by over $6 per megawatt hour. And then as we step through to the full US model, starting just with existing interregional transmission, costs continue to decline. And then as we add new interregional, and then finally, including new DC transmission across the interconnects, so connecting the Eastern and Western, and then Texas with the Eastern, the cost continues to decline as the ability to deploy this interstate and interregional transmission increases. And in general, across each of these cases, you get about 8 times larger reduction in the system cost of electricity compared to the amount that you're spending these new slivers in the levelized transmission costs. So that's not all that's changing. As you're adding new transmission to the system, the other capacity mix on the system is also changing. So in particular, as you add transmission, the amount of storage energy capacity deployed decreases quite rapidly. So you require only about 1/4 of their transmission for the US, allowing new transmission between planning areas compared to the isolated states case. The total generation capacity also decreases. So if you would compare the fully interconnected US with the isolated planning areas, you're installing about 600 gigawatts less PV and wind than you would if you weren't allowed to connect those planning areas. The energy mix is roughly 50-50 between PV and wind in each of these cases. But the available energy, so that's the capacity factor of the installed PV and wind sources times the capacity that's installed, decreases as you increase the transmission capacity. And so on this plot, the total annual demand is shown here as the dashed line. And so energy above that is curtailment. And so there is a good bit of curtailment here, but I'll talk about that a bit more in a couple slides. I don't think it's the most useful metric to focus on, but we do really rely on having a lot of that excess energy to meet demand during periods of low resource quality or low resource availability. So looking at the values that you can see for transmission in this study, there's kind of 2 major values that we see at our resolution. The first is that as you interconnect geographic areas over a larger scale, you get a reduction in the aggregate variability of PV and wind. That's partially able to be seen through this previous slide, so the reduction in storage energy. Also, if you look at the duration of storage that's installed, so here we take the energy capacity of storage in each planning area divided by the power capacity to get a duration in hours. So starting with the US, where we don't allow new transmission between planning areas, we just use the existing transmission. You get up to a 16-hour duration storage in some regions and average around 10 or 12. And then as you allow new transmission expansion between the planning areas, that goes down to maybe average around 8 hours. The second benefit is that by being able to connect areas that are farther apart, you have better access to higher quality resource regions, and that means that you get more energy from less PV and wind capacity. And that's most notably seen comparing the isolated planning areas with the first of the US cases. So you can see that you install more generation capacity of combined wind and solar in the planning areas than you do in the full US case, but you actually generate more energy from those resources in the US case. So yes, you're increasing curtailment, so the gap between the top of the bars and the dotted line, but you're reducing the cost and reducing the total capacity installed, reducing the land intensity of those wind and solar resources. And so I think it's, in this case, more helpful to focus on this kind of optimal wind and solar build out, which does increase curtailment, as opposed to just trying to reduce curtailment. There's also additional benefits of transmission that we don't resolve at our resolution. So things like sub-hourly balancing, reduction in forecast uncertainty. So these top two are really just the ones that we can see at our resolution. Now, everything I've shown so far is kind of for a central selection of assumptions about the cost of new resources and their availability, the cost of transmission, mostly based on the NREL annual technology baseline. Of course, a lot of these parameters are quite uncertain as you look to the future. And so we do a sensitivity analysis looking at how might these results change if you vary these assumptions. And these are the same metrics that we showed on earlier slides. To start with, you could say, well, what if we're way low on our transmission costs? We use the central cost from the Reeds model for transmission dollars per megawatt mile, but what if we're 2x or 5x too low? Then you see that even if you increase the assumed transmission cost by 5x, you're still increasing transmission deployment compared to a no new transmission allowed case, and you're still reducing the system cost of electricity. If you include brownfield assets, so the existing nuclear, that does reduce the cost a little bit. Comparing that to installing new nuclear at either Vogel costs around $12,000 per kilowatt or the central ATB assumptions around $6,000, they don't have that big of an effect on the total system cost of electricity. You have to reduce nuclear costs to about $4,000 or $5,000 per kilowatt in order to kind of noticeably reduce those costs. The three lowest cost scenarios that we find are this the quite low cost nuclear case, the case where you achieve the annual technology baseline's low estimates for wind and solar and lithium ion, and then a case where we reduce the energy cost of storage to $5 per kilowatt hour, what you might call a long duration energy storage. I won't talk too much about it, but the wind assumptions we found are quite important. So we're modeling a low specific power, kind of low wind speed optimized turbine. If you installed higher wind speed turbines everywhere, then the amount of storage and the system cost of electricity would both increase quite a bit. In terms of electricity demand assumptions, certainly if you increase electrification, so this is the high electrification case from NREL's electrification features study, you're increasing the capacity and the total amount of energy. But since you're normalizing that over a large amount of energy, you're not actually changing the system cost of electricity in terms of dollars per megawatt hour all that much. We looked at changing the VRE, the wind and solar land availability assumptions. And even if you reduce the available land by a factor of 2 or a factor of 5, there isn't too much change as long as you can install new transmission across areas. Once you start getting to a 90% reduction, then the cost does start to increase more. I'll skip the reliability just in the interest of time. Coming back to this curtailment point, it's kind of interesting to compare no policy cases where we allow combined cycle gas turbines shown in brown with the baseline case, which is zero carbon. And so if you hold these gas assets to the same standard and quantify their available energy as their capacity times, in this case, complete hourly availability, it basically looks pretty similar to what you get for the baseline zero carbon case. So just as you overbuild gas capacity so that you have peaking capacity available to meet those few hours of peak demand, you're also overbuilding your PV and wind, basically sizing them for low resource times such that you have more than you need in high resource times, but you have the ability to meet demand in lower resource times. And maybe the main point here is that even across all these different scenarios, we see that each of these scenarios for the full US allowing new transmission is cheaper than the isolated planning area scenario, so not allowing new transmission between planning areas. So that really just emphasizes the value of this interregional transmission for zero carbon systems between planning areas. Now, all of that was for the case where we look at the whole US and allowing new transmission, but the sensitivity to these different assumptions varies depending on that transmission assumption. So here we've taken a subset of these sensitivity cases and then run them with the 6 transmission scenarios shown up here. And in general, across all these cases, we see that costs uniformly increase as you go from the case that allows new transmission up to restricting the amount of transmission up through the state's case. But the impact of transmission varies depending on your other assumptions. So as we mentioned, the lowest cost case across all scenarios is achieving the ATB's low cost projections for wind, solar, and lithium ion, along with allowing new transmission installations. But if you aren't able to install new transmission either between planning areas or within planning areas, then the lowest cost cases are this flexible nuclear at $4,000 per kilowatt, or the long duration energy storage at $5 per kilowatt hour. And so this kind of explains how, depending on the geographic resolution of a study, you can get sort of different indications of what might be most important. So if you're looking at isolated states or isolated regions, then a long duration storage or flexible nuclear look very important. But if you're allowed to expand new transmission, then reducing the cost of renewables tends to look more important. The other thing just to point out is that that this highlights is that there are multiple potential paths to a low-cost zero carbon system for the US. This dotted line is 7 cents per kilowatt hour, which is roughly the LCOE of coal. So if you say cheaper than coal counts as low cost, then there are numerous ways to get there across a range of assumptions. I don't see the timer. How am I looking on time?
I'm about 1 minute.
Yeah.
Okay. All right. I will skip a few details on interannual variability, but include them in the slides that are shared. So the last point I'll make is that while costs do increase non-linearly as you're going, as you approach this 100% renewables target, it's a bigger issue for isolated areas than for the US as a whole. So here I'm showing the isolated state case, showing the 7-year solution at zero carbon for each state as the blue bar. And then this overlaid black line are sub 100% clean energy standards. So looking at 0% on the left, and then up to 95, 99, and 100% on the right. And so you see for isolated states, the cost of this last bit of decarbonization can be quite large. So for some states, it doubles the cost going from 99% to 100% renewables based on the resources we include here. If you compare that to the full US allowing new transmission, then there is still a nonlinear cost increase, but the degree of that increase is much smaller than for isolated states. And so if you're looking at how far you can go, reaching 100% for the full US is about as expensive as reaching 95% at the state-by-state level. So just to conclude, we do see that zero carbon electricity systems based on technologies currently deployed at gigawatt scale are feasible at hourly resolution over multiple years for the US. And that increasing or allowing new transmission to be deployed between planning areas can significantly reduce that cost. We do see that if transmission is restricted, then having flexible resources, either flexible nuclear or long duration energy storage, can reduce the cost. But we can't really say that they're required, given that we could get to a lower cost given currently available resources and transmission. And then finally, the decarbonization costs are quite a bit lower if you're looking at decarbonizing the US with a kind of centrally optimized approach, as opposed to an every state or an every region for itself. So with that, I'll just thank my co-author, Autumn Bouterud, and a lot of other members at the MIT Energy Initiative for helpful discussions. And the paper is available here, and looking forward to the Q&A. Thanks.
Great. Thanks so much, Patrick. Charlie, I failed at my task as chair because you wanted me to do the pitch after the DLR presentation for the upcoming webinar, E-Cig monthly webinar on April 20th, because it will be presenting topics on grid enhancing technologies. So everybody put that on their calendar and visit the E-Cig website for further information. It'll be looking at methodology and key findings from a new study that model dynamic line ratings, advanced topology control, and advanced power flow control on the Southwest Power Pool system. So again, April 20th. So Charlie, if I'm fired, just send me my paycheck. But anyway, with that, it's hard to get fired from this role, huh? With that, we will, I guess, bring the panelists back and start looking through some of the questions. The first one, I think, is probably towards Morgan, if anybody can answer. But what are the challenges of buried cables over overhead lines? How do you recommend overcoming challenges such as fault location and fast repair and restoration?
That's a great question. I should note, if that wasn't obvious from my presentation, that I'm not an expert in restoration and repair. I do believe it's possible. We have underground infrastructure. There are people who could probably tell you the exact ways that we would address that challenge. I am focused more on the high level narrative and tying together the policy pieces. I do want to get into these details because I don't think they are details that can be glossed over. And so to that end, some of the work that I'm doing in the coming months is to get to that, but I don't particularly I don't have a specific answer today on the restoration repair. So.
I do know it's a topic of interest, especially on undersea cables. There's been a lot of discussion by the HVDC vendors in general about fault location, because that can actually sometimes increase the amount of time to repair, just finding the fault. But but it is a hot topic of research as HVDC cable systems get more and more gain more and more interest and application.
Yeah. Thanks, Wayne.
So the next one is, I think, for David or Joey. No downtime with Ampacimon means that the equipment can be installed by a live line crew while the line is energized. Question, I guess they're asking for clarification on that question.
Hey, yeah, can you guys?
And I can clarify.
Oh, yeah, go ahead, Dave. Go ahead.
No, I was just going to say, so that is what I meant. So basically, the sensors can be installed on the line live without the need for an outage.
Thank you. So Patrick, this next one's for you. Have you compared offshore wind versus large interconnected HVDC lines to meet the renewable requirements? Some states are taking an offshore wind approach.
Yeah, it's an interesting question. We would love to look at that here. As I mentioned, we kind of had this upfront framing for the study looking at technologies that are currently deployed at gigawatt scale in the US. Currently, there's only about 30 megawatts of offshore wind, and so our confidence in the cost numbers are much lower than for other resources. So we left it out of this kind of quite conservative study, but a lot of the data is available through these same resources from NREL, the Wind Toolkit, for example. And so I think it'd be a great follow-on work. And so, yeah, it'll be exciting to see, how much we're able to grow from that small 30 megawatts now to the multi-gigawatts that are currently planned. But yeah, it was not part of this study though.
So another question, and assuming towards Morgan, but whoever might have experience with this, feel free to answer. Are there issues with induced currents in pipelines co-located with electric transmission line routes? This is a major challenge in Germany.
Yeah, so this one I actually know a little bit about, and we've been working, and we, being myself and the Ray, with Southwire, who purchased ABB's cable manufacturing business. And what I would tell you is that the older HVDC designs had this issue, the newer ones don't. So there's a bipole line with a ground current return line, and that basically alleviates this essentially what is a historical concern that is no longer an issue with new HVDC designs.
Yeah, my understanding too, well, is that, if you try and, in general, siting of ground return is nearly impossible, period, Europe or elsewhere. Like the older systems that had ground return, you just won't see those happening anymore. Earth ground return. So.
Right. Yeah.
So again, Morgan, is Sugreen a fair representation of HVDC costs? There are no flyover states, and therefore no required, intermittent converter stations or midpoint converter stations.
Yeah, I think that's a great question. For me, that's really where the transportation electrification element starts to tie in. So when we talk about converter stations today from a 500 kV line, we sort of go, it's economical if you have a multi-gigawatt load, so a couple gigawatt load to build a converter station. In the future, I think we are going to get to the point where we're looking at converter stations that can connect to such a line when we're only serving a few hundred megawatts of load. So what becomes interesting to me is to think about how to eliminate the flyover state problem by delivering something like a data center or a collection of data centers that are sited along this line and also co-located with renewables and why not some EV charging, and basically have sort of a multi-hundred megawatt load that needs the resiliency that this line can offer, that would benefit from the fiber you can co-locate with this line, and basically use that to eliminate the flyover aspect. And I sort of alluded to cost, and maybe to come back to it for a second. As a person who started their career in the solar cell industry, we're talking about a semiconductor technology when we're talking about these HVDC converter stations. And so given that, I think that as we scale up the deployments of HVDC converter stations with the new VSC technology, that we will see a cost decline. And that is what will enable these sort of multi-hundred megawatt loads to be connected.
And my understanding is, the VSC is also much, there's there's one or two examples of LCC that are multi-terminal, but there is kind of a threshold size for the midpoint terminals. But with VSC, you don't really have that same challenge. So, but again, the commercial aspect becomes the challenging part. So, so let's see. There was one, let's see, Patrick, could you describe how different energy resource components you considered could interfere with further transmission expansion development?
Yeah, if this is about the land usage, then I would say for solar, there's really no competition. The shading from transmission lines is really wouldn't affect the solar output. For wind, most of the wind area that we account for here is empty space, spacing between turbines. We did show in one of the sensitivity cases what would happen if you reduce the available land area for wind and solar by a factor of 2 or a factor of 5. It really didn't impact the cost that much, and you build even more transmission if you reduce the available land area for wind and solar. So I don't think, if that's what the question is about, I don't think that the land usage is that big of an impact. There's certainly the permitting and cost allocation and all that for transmission, which makes it tough. But in terms of the acres of land used, you're using more for renewables, much more than you are for the transmission. And in general, just the one other piece here is that we do see that wind and transmission basically play together the nicest, and then solar and storage play together the nicest. So if you are looking at things that help or hurt wind, then those will also help or hurt transmission. So those fates are kind of linked.
So David, is there a threshold above which DLR solutions aren't enough to solve the problem?
It's a case-by-case basis for each line. What I'll say is, for us, the Harwood-Susquehanna line, it alleviated just about all of the congestion from our own calculations and studies. Really, PJM's the authority on that. They're our RTO. But the other line that we applied it to, it didn't alleviate 100% of the congestion. We started to run into just limitations with, hey, this is the most we can get on the line rating, and that equates to a certain percentage of congestion. And what you also start to run into is, if the line is the limiting component, you start to run into whatever the second most limiting component is, which may become the foremost. But from what we've seen so far in our experience, it's really a case-by-case basis. That's for each line.
Thanks. Joey and David, are there opportunities for other transmission asset owners in PJM?
It's hard for me to, and I don't know if Joey would like to chime in, but it's hard for me to speak for other transmission owners. I'll just speak for PPL. We really did see this as a beneficial technology. We are getting benefits from it, and it's something that we're going to continue to pursue. I can't speak for others, but there may be.
Yeah, I mean, I think if you do look at, not just PJM, but the other RTOs, there's many transmission lines that have multi-million-dollar annual congestion costs per year that they could benefit from doing this, and it creates a situation that's more financially advantageous to the end consumer. And so in the end, yes, there are many other opportunities that this could be applied to in PJM and other places as well.
Okay, so Joey, how quickly will a line heat up if you have assumed wind cooling but anticipated wind drops?
Oh goodness, I need some input variables to make that calculation. So, as you know, the conductor does have its own specific thermal inertia, and so you're right in stating that it will take time for that line to heat up. However, we have safeguards against that in our system. So the ratings are all updated every 5 minutes. So anytime there's changes in conditions, that rating gets updated. So you're not sitting there operating for more than 5 minutes if the wind has changed on a different rating. Definitely greater than 5 minutes. I would, if I were to give an estimate, it really depends on the conductor. It depends on the wind speed. It depends on the ambient temperature. But I would say anywhere from 30 minutes to several hours. It's kind of hard to say without knowing what the conditions are. But the key thing is we continuously monitor and we update it every 5 minutes. So you're not stuck with using an old condition.
I'd be interested maybe if you could kind of just talk a little bit more, kind of how your thinking is or went through for kind of your procedure, because I remember, and this has been a decade and a half ago at least, when I was at Southwest Power Pool, we had experimented on one of the major flow gates there with some dynamic line ratings, and what we started finding was we thought initially it would reduce the number. At that time, we were using TLRs through the NERC IDC, and we thought it would reduce the number of TLR5s. And what we found is in the summer, the rating would quickly drop below its static rating. It's a little bit of a calculation issue, but like what can you kind of talk us through maybe y'all's thinking process on standard development around that? Because I think that's critical, right? What is your assumption when it's full sun and zero wind and it's the highest load point of the day?
Yeah, so what we do is we do not take the static rating as the lowest possible rating. And as a matter of fact, if we look at all the different lines systems we've deployed, anywhere between 2 and 5% of the time, the actual rating of the line goes below static. It's not always true, and a lot of times it also depends on how aggressive the asset owner was when they produced the static rating. And so, I'll kind of turn the question around in a different way. It's like if you're not monitoring this, the environment could create some conditions where your static is too high, and you're operating out of your limits. You just don't know it.
Right. Yeah. All right. Very true. Okay, I think we have time for one more here. So I'm assuming this is maybe to Patrick, but maybe to the whole panel here. The nonlinear cost for 99 to 100% zero carbon energy open up opportunities for technologies that would otherwise not be cost competitive, green hydrogen, gas CCS, etc. So I'm guessing by nonlinear cost, they mean just the incremental cost to go from 99 to 100. But.
Right. Yeah, so we didn't include them here because we were trying to be conservative about things that are employed at gigawatt scale today. But the results we showed for long duration energy storage here, they're modeled on pumped hydro, but having a similar energy capital cost versus power capital cost for green hydrogen or something where energy capital cost is low but power is high, it's kind of similar to pumped hydro. You would probably get similar results there. And so that was, I think, the second cheapest scenario that we found in our study is making that kind of long duration storage available. So yeah, I think it's definitely worth continued work on that. For CCS, I think there is the question of the high fixed costs and how you would recover them for keeping the gas pipeline network around and building a new network for CO2 transport and storage and everything. And so using it for just the last 1%, if building up a whole network for that, you would need to consider that whole life cycle cost. But yeah, so I think a lot of these things are definitely important for pilot projects and looking at them. That being said, I don't think we should lose sight of the fact that a whole range of studies, our study, the Princeton study, a lot of NREL studies identified that we were pretty sure about the first 90%, that it's a lot of wind, solar, and transmission. And so, these last few percent questions are quite interesting, but I think there's wide agreement on just deploying more primarily wind and solar now in the short term. And then as we go, we'll have a clearer and clearer picture of what some of these, technologies for the last few percent are. And, in the middle of rapidly deploying technologies we have now, we can do pilot projects for these new types of projects, while not losing sight of, the urgency to deploy the resources we already have.
Okay. So with that, I think it's about to wrap things up. And I'd like to thank our panelists for their great presentations and discussion today. Thank all of you for your participation. I think we've seen some great insights here into the evolving transmission landscape. I hope it's provided some stimulating food for thought for everyone. As a reminder, we will follow up with written answers to the Q&As we didn't get to during this time. I did notice that I think I have a rogue transmission planner that threw some questions in there for me to maybe test my knowledge. If I find out who that was, they might be in trouble. But anyway, I would like to remind you that the spring workshop sessions are being held on Tuesdays and Thursdays through April 8th. We have a session next Tuesday on distribution system planning. Again, there's no charge for these sessions. You're all invited to attend, and further information and registration can be, as well as the April 20th webinar, which was posted in the chat session there, are available on the E-Cig website at www.ecig.energy. So thanks again, everyone. Stay safe out there, and look forward to seeing you again on Tuesday. Everyone have a great day.